So in the last lecture, we went through some recurrence relations to describe the running time of algorithms. And you have recursive algorithms, they generate these recurrence relations. It was quite tedious. It wasn't a lot of fun. You had to do a lot of algebra. It was complex. We're now going to make your life a lot easier. We have a theorem called the master theorem that will help you out a bunch. Okay, so what is the master theorem? The master theorem imagines that you're given some recurrence relation of the form T of n equals a, some positive number a, times T of n over b has to be larger than 1, plus O of n to the d, some quantity O of n to the d, and d has to be at least as big as 0. Okay, so we imagine we have this recurrence. The master theorem is going to answer what is the actual growth rate of T of n precisely. Let's do that right now. So this recurrence will solve to one of three possible cases. If a over b to the d is less than 1, strictly less than 1, then the recurrence solves to O of n to the d. That's the growth rate of T of n. If a over b to the d actually equals 1, then the recurrence solves to O of n to the d with a log n term. And if a over b to the d is strictly greater than 1, then you end up getting, the recurrence ends up solving to O of n to the log base b of a. And you can simply ignore d in that case. Okay, so this theorem looks perhaps a little complicated. You have three different cases. Where did this come from? It turns out we've actually already done basically enough work to understand how to prove this theorem. So let's just give a little sketch now, and I think you'll get the idea. Just remember how we expanded out those recursions before, right? We first got the first term times some constant c, plus a times, and then we kept expanding, right? C times n over b to the d, because now we have n over b once you go one step deeper, plus a times yada, 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 yada. We get a t times t of n over b to the I, and so forth. Once we collect all the terms appropriately, though, we end up getting a c times n to the d times this geometric series here. And how far does this geometric series go? Well, it goes as many times as you need to have this recursion bottom out. What does bottoming out mean? You have to get to the point where n over b to the I is a constant, let's say 1. And that occurs, of course, when I is equal to log base b of n. This log base b of n is the number of steps you have to go until you get n over b to the I to equal 1, right? And then, of course, you had this second term, which was a to the log base b of n times t of 1, since now you've gotten this recursion down. You've had it bottom out, right? Now the question is, how do we understand this quantity right here? We have a term on the left, a term on the right, and now we just have to reason about what this quantity is. Okay, the first thing we can do is notice that this term right here, a to the log base b of n times t of 1, remember t of 1 is just O of 1, that's a constant. So this whole thing can be written as O of n to the log base b of a. That's just using the log manipulation we taught you in a previous lecture. You can check that for yourself. So let's also just now consider, I don't know, let's say one case. Let's consider the first case. If it's the case that a over b to the d is strictly less than 1, then it's important to notice that this geometric series right here, well, you have a geometric series where the base is less than 1. That means this whole thing is bounded by a constant. Therefore, we have this term right here is going to be on the order of n to the d, because this guy right here is a constant. We have n to the d here, and then we have another constant again because a over b to the d is less than 1. So this whole thing is bounded by a constant. Of course, then we have plus O of n to the log base b of a from this term up here. Okay, but what is n to the log base b of a? We know that just following this statement right here, if a over b to the d is less than 1, right, then we can also conclude that a is less than b to the d, which also implies that log base b of a is less than d. And if that's true, that means that O of n to the d, well, I guess I can say simply n to the log base b of a is equal to O of n to the d, right? It has to be less than n to the d because the exponents are smaller. D is a larger exponent than log base b of a. So log base b of a is swallowed by the O of n to the d term. In other words, this whole thing is equal to O of n to the d. Okay, so if it turns out that a over b to the d actually equals 1, then things are a little bit more interesting, because that means that this geometric series here, well, that's just 1 plus 1 plus 1 plus dot 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 plus 1 log base b of n many times. So you end up getting an expression which is t of n equals O of n to the d times log n, right? That log n comes from the fact that this geometric series is actually just a bunch of ones. 1, 1, 1, 1, 1. But how many of them? Log base b of n many times. I think there technically should be maybe a minus 1 here, but that doesn't really change the actual order very much. And similarly, you'll notice that we have to include this plus n to the log base b of a, put O of here, right, which comes from this term over here. We can't forget this term over here. But n to the log base b of a, as we discovered, in this case we'll have, thinking back to the last case, log base b of a is actually equal to d. This is, of course, equal to, this whole thing is going to be equal to O of n to the d log n plus O of n to the d. You can check that log base b of a is going to equal d in this case because of the condition that we're looking at. Because of this condition right here, log base b of a is actually equal to d. So this term in the end isn't actually relevant. The whole thing is just O of n to the d log n. Okay, so the last one, if a over b to the d is strictly greater than 1, well, you know what? I'm going to leave that one as an exercise. It's a good exercise, so try it at home. Did you know that the word of the day is kangaroo? Well, now you know, it's kangaroo. Okay, so now that we've taught you the master theorem, it's important that we actually show you how to use this in practice. Let's consider a couple of examples. Some you've seen and some you haven't seen. So, you know, one of the most basic algorithms, I guess we haven't actually done this precisely, although we may get to this, binary search. In binary search, right, you have a list of n numbers that are sorted, and you want to find if one number exists in the list, or maybe you want to like find the position of that number, right? And what you do is you check the midpoint, and you see if the number you're looking for is either above or below what that midpoint is. And if you find that it's above, you can throw away the bottom half of the list. If you find that's below, you can throw away the top half of the list, which means that you have a constant number of operations on every round. But you get to reduce the size of the list by a factor of 2. So the recurrence is t of n equals O of 1, right, a constant number of operations in every step, plus t of n over 2, right? In this case, let's just plug in the numbers, right? Here we have, so here we have a equals 1, we have b equals 2, right? Because it's n over 2. And we have d equals 0 in this case. So what does that imply? That implies, so now we have to check, is a over b to the d greater than 1? And in this case, a over b to the d is 1 over 1, in which case we are in the sort of second case for the master theorem. So we end up getting t of n equals O of n to the 0 log n, or just O of log n. Good. Okay, how about merge sort? Right, there we had t of n equals O of n plus 2 times t of n over 2. right? You had to break the list into two halves, sort each sublist, and then merge the two sublists. The O of n operation is the merging of those two sublists. Now we have now we have A equals, what do we have? A equals 2, B equals 2, and D equals 1, right? So what is A over B to the D? A over B to the D equals, looks like equals 1, right? A over B to the D equals 1. Therefore, we are again in the second case, and therefore we have T of n equals n to the D log n. So that's O of n to the 1 log n, right? Which is n log n, which is what we expected for sorting algorithms, n log n, on the order of n log n. Okay, how about that standard multiplication, right? Just like multiplication, let's say not fast. Here we had T of n equals 4 times T of n over 2. Of course, we went through this in detail, but let's just use the master theorem now. We'll see how easy it is. Plus O of n. Okay, so here we have A equals 4, B equals 2, D equals 1. So A over B to the D, A over B to the D equals 2 in this case. That's greater than 1. So we end up having to use the last case, T of n equals O of n to the log base b. What is b in this case too? Log base 2 of 4, right? And what's the log base 2 of 4? Of course, this whole thing equals on the order of n squared. Good.